Okay, good morning, everyone. Okay, hope you had a good weekend and you didn't have any pre-lecture to watch today, so I bet you guys are happy about that. Just a reminder, when it comes to the midterm next week, we're only doing stuff from week 6, so after the last midterm up until today's lecture, okay? So from Wednesday into next week, we're going to be looking at nonlinear systems, but those nonlinear systems are not going to be on the midterm, they're going to be on the final instead, okay? So this is the last set of material today that goes on midterm 2. So we're going to be continuing to talk about linear systems. You guys are probably wondering why this is called Romeo and Juliet. I'll get to that in a minute. So far, when we've been talking about linear systems, we've been talking a lot about the methods, thinking about complex eigenvalues, real eigenvalues, what this means in terms of, say, the trace and the determinant of our matrix that forms our linear system, for classifying stability, so whether we get things like nodes or spirals or centers or saddles, and whether they're stable or unstable. But we haven't really talked that much about what those the variables within our models actually represent. Okay, and when we're talking about our nonlinear systems from Wednesday onwards, most of the time we're going to be thinking about population sizes. So our x1 and x2 would represent a number of, say, predator or prey individuals in the population. But with our linear systems, because if I draw on here, if this is my x1, x2, when we've been drawing our phase planes, when we're doing our nonlinear systems, we're mostly going to be up in this quadrant here, because we're talking about population sizes, so we'll be talking about non-negative values. But we've been talking so far about having an equilibrium at the origin, and maybe you spiral in or you spiral out, or you could approach it from various directions. Now, in principle, if you just restricted yourself to this top right quadrant, then you could talk about them as being population sizes. But for the most part, we've been thinking about positive and negative values of this x1 and x2. So what can they represent? Well, one thing they could represent is some sort of movement in space. So if your origin is a reference point, suppose it's the den for a pack of wolves, the model might represent their movement patterns. And so, you know, do they return to their den? How often do they return? Things like that. It might represent some sort of foraging patterns for herbivores through the different seasons. So we could think of it as a spatial location and having a reference point, therefore you can take positive and negative values. We can also think about behavior. So, for example, x1 and x2 could represent how antagonistic or mutualistic two species are towards one another. Okay, so positive values could be positive interactions, so they are mutualistic or beneficial towards each other, negative, antagonistic towards each other. Okay, so the relationship between these two species or two individuals might change. So they might change over an ecological time scale, so just over the course of those individuals interacting with each other. How the other one interacts with it might affect how it interacts with it in the future. They also might vary over evolutionary timescales. These could be two co-evolving species, and they have heritable traits where the x1 and x2 represent how antagonistic or how mutualistic they are. So with these linear models, they can be good representations of things like movement and behavior, as well as long-term evolutionary dynamics. So where does this bring us to today? And what's that have to do with Romeo and Juliet? There's a famous, slightly silly model in the 80s, I believe, where people talked about mathematical models for love. And so Romeo and Juliet being the archetypal story of two star-crossed lovers, this kind of became set in stone, and people talk about it as or use it as a demonstration for how these linear systems can be used to model changes in behavior in simple populations. Okay, so we're not actually going to talk about meta populations today. I'm going to scrub that out. Okay, so what is this mathematical model for love? So this is the Strogatz model from the 80s. Like I said, it's been around for quite a while. And here we're going to say that this capital R at time t represents Romeo's love or hate for Juliet. It's this kind of retelling of the story. And J of t is going to be likewise Juliet's love or hate. So when R or J is positive, we're going to have them in love with each other, or one in love with the other at least. And when they're negative, they hate each other. Okay, so we're going to assume that there's a feedback between their feelings towards each other. And we're going to suppose that Romeo's feelings change in proportion to how Juliet feels about him, but Juliet's the opposite. The more he declares his love, the less she likes him. Okay, so how do we write down a model for this relationship? Well, we're going to want to have a drdt and a djdt, and these are going to tell us how their feelings are changing over time. And we're told that Romeo's feelings change in proportion to how Juliet feels. So what does that proportion mean? Well, we don't know what the proportion is, like how much they change, but we can say there's some positive constant A minus by J. So however strong Juliet's feelings are, there's some proportional change in Romeo's feelings, okay? So if she loves him, he loves her more. If she hates him, he hates her more. We're told that Juliet's the opposite. Again, her feelings change in proportion, but in proportion to Romeo's in the opposite direction. So I'm going to set this to be minus BR. So the JDT is minus BR, where we've got this A and this B are just positive constants. We don't know what they are, so we're just going to have to talk about our model in terms of whatever these constants happen to be. Okay, so we've got a linear system now. So that means that we can sketch solutions using phase planes. We can also look at the trace, or set this up as a matrix vector equation, and look at the trace and determinant to work out what the stability of my origin is going to be. So that's looking at the long-term behavior of the system, looking at our eigenvalues. So just to write this in matrix form, we set X to be our vector. So I'm going to set X to be Rj. Like when we did our population models before, it doesn't matter the order I use as long as I'm consistent. So I could have done JR. I'm going to do Rj here. Here we have 0A minus B 0 times by R X. Okay, so what I want you guys to do is, using what we did in the last couple of lectures, remember we had, if I just go back to it quickly, we had this diagram here, which tells us if we look at the trace and the determinant of that matrix, what our dynamics are going to be in the long term. Also, we did quite a lot of drawing of phase planes. So have a go at drawing phase planes for this and looking back at the trace and the determinant to figure out what goes on in this model of love. I will put it back up on the screen. Okay, have a go at that and I'll walk around and answer some questions. Okay, I'm not seeing many phase planes as I'm walking around, so I'm going to go through this with you guys. Okay. So what I'm going to do first of all, actually, is I'm just going to look at my trace and determinant, because that will tell me what I should be drawing. Okay, so if I look at my trace, which I'm going to call tau, so the trace of my matrix A, I'll call this A. So we've just got 0 and 0 on the main diagonal. So this is 0. If I look at my determinant, we have 0 times by 0 minus minus B times by A. So we're going to have plus AB. And since A and B are both positive, this is going to be positive. So let's go back to the diagram from before. We have the trace being equal to 0 and the determinant being positive. So that means we are up here. That means we have a center. Okay. So let's go back. So we have a center. So it tells me that there's something's going to be circling around. It's kind of a good stage to do either before or after you do your phase planes. Go back and check the trace and the determinant. It doesn't take very long to work them out, but it's pretty handy for making sure that you've drawn the right thing. Okay, so whenever we're doing a phase plane, the first thing we need to think about are our null lines. Remember, our null lines are where we have dr dt is equal to 0 or dj dt is equal to 0. So when it's dr dt equal to 0, well, that means we need a times by j to be equal to 0. And since a is positive, that means j is equal to 0. So that means that we have a null line here where j is equal to 0. I'm just going to color code this rather than having too much on this. Okay, let's think about our dj dt is equal to 0. Well, there we have minus br is equal to 0. And since b is positive, this means that r must have to equal 0. That means that my other null line is here. And the intersect at the origin, that's our equilibrium for the system. So that's my second null line. So once I've found the null lines, what do I have to do next? Sorry? Arrows? Yep. So we need to find our direction field. Okay, so what are the arrows, our direction field? At this point, before I even do any calculations, I like to actually just draw on arrows onto my diagram anyway. On the green null line, we know that dj dt is equal to 0. So that means that we can't be moving up or down. So that means that we have to be moving left or right. I don't know which way we're going yet, but I know we're moving left or right. And then on the pink null line, dr dt is equal to 0, so we can't be moving left or right there. We have to be just moving up or down. Okay. It's useful to do that at that stage because it helps make sure that you don't accidentally put the arrows on the wrong thing. So I don't accidentally put vertical arrows on the green null line and vice versa. Okay, so what do we do for our direction field? On our direction field, we're interested in looking at what is the direction of our j or our r variable when we are on one of those null lines. Okay, so I'm going to pick the pink one first of all. So on the line j is equal to 0, so that's the pink line. We know already that dr dt is equal to 0. Okay, so we must be moving up or down. So let's look at dj dt. And we know that dj dt is equal to minus b times by r. Okay, it turns out this doesn't depend on j at all anyway. So what this tells me is that dj dt is negative if r is positive, and it's positive if r is negative. Okay, so all I'm interested here is the sign of my dj dt depending on the sign of whatever is on the right-hand side. Okay, so I'm interested in how dj dt varies as the sign of r changes. Why do I care about that? Well, dj dt being less than 0 means that our arrows are pointing down, j is decreasing. So we know that dj dt is less than 0 if r is greater than 0. R is greater than 0 over this side. So that means these arrows point down. And dj dt is positive if r is less than 0. R is less than 0 over this side. These arrows point up. Note that as we pass through from one side to the other, if we're traveling along this pink line, as we go through our equilibrium at the origin, the direction changes of our arrows. Okay. So if you find that the direction doesn't change, if I, for example, had something like this, that's a problem. Okay. The direction of my arrows will be changing as I go through this equilibrium for all the cases we're going to look at in this course. Okay, so that's the first null line. I do exactly the same on the other. So on the line r is equal to 0, what do we know? Well, we know that dj dt is equal to 0 by definition, because it's a null line for our variable j. That means we must be moving left or right. And what's our dr dt? Our dr dt is equal to a times by j. And in this case, it doesn't actually depend on r at all. If it did, we would just substitute this into this equation here. So what does this tell us then? It tells us that dr dt even, dr dt is positive if j is positive, and it's negative if j is negative. So it's the same sign as j. So when is j positive? J is positive up here in the top part of my graph. So when j is positive, the rt is positive, so we're moving to the right. So these arrows go like this. When is j negative? J is negative down here in the bottom part of my graph. When j is negative, dr dt is negative, so we move to the left. Again, as we pass through, if you walk down that green line or go up it, as you go through the origin, the direction of these arrows changes, okay? So at this point, suppose I hadn't done the previous analysis, I'd just drawn this phase plane. I know that there's some sort of oscillation going on here, right? I know that things are kind of spiraling, and we know that they're going in this direction. But just from this phase plane here, I don't know whether things are spiraling in or spiraling out, or if they're staying the same. So that's where looking at my trace and my determinant, and potentially my trace squared minus 4 times my determinant, tells me about the stability of these oscillations. So I know here from this analysis that I have a center, and that means that I'm neither spiraling in nor spiraling out. So that means if I choose a starting point, say here, I go around like this, and I keep going around like that forever. If I start in here, I go around like this. Okay, so what's the actual interpretation of this? Well, when j and r are positive, we have that Juliet loves Romeo and Romeo loves Juliet. But we see that doesn't last for very long. Eventually, down in this region, Juliet hates Romeo, but Romeo still loves Juliet. Then over in the bottom left quadrant, we have them both hating each other. And then the top left one, Jade becomes positive again, so Juliet loves Romeo, but Romeo still hates her. And then they go back to the start. So if I was describing what happens if I say start in this positive quadrant, I would say they start off loving each other, but then Juliet hates Romeo. Then Romeo follows her and then hates her. Juliet starts loving Romeo again, but Romeo still hates her. And then eventually Romeo follows suit and they're back in love again. And they spiral on like this. What's the long-term behavior? Well, because they're neither spiraling in or spiraling out, they just keep going around in this circle forever, okay? So they keep loving and hating each other and it never ends. Sorry? Did someone? It dies when they die. I mean, yeah, that's a lovely nihilistic view of nothing matters, we all die in the end. Great. Sorry, question. Yes, exactly. Yes. Exactly. That's a very good question, because when we do our nonlinear systems, we're not going to just have equilibria at our origin. Okay, they will be elsewhere. In all of our linear systems, and all the ones we'll look at for the linear part, you always have just one equilibrium at the origin. When we do our nonlinear systems, we get moved away from the origin. Okay, a very good question. Any other questions? Okay, like I said, we'll be doing nonlinear systems. We'll be doing a lot more of this, like drawing phase plane stuff. So practice, practice, practice. with that in mind, let's have another look at a slightly different Romeo and Juliet model. Okay, so now suppose that they're a bit cautious. So rather than just responding to the other one's feelings, they try not to let their own feelings run away and are responsive to the other person. Okay, so this time we can have Romeo's feelings are negatively correlated with his own and positively correlated with Juliet's. Juliet's are positively correlated with Romeo's and are negatively correlated with her own. Okay, so they try to be responsive. We're also going to stipulate here that A and B are not equal to each other. Okay, so here we need to explain the dynamics in this situation. So let's first write down it in matrix form. Here we're going to have minus A, B, B minus A. My RJ. I'm going to call this matrix A. Okay, so let's think about our trace and determinant to start with. So my trace of this matrix is going to be minus A, so it's just going to be minus 2A. We're told in the question that A is positive, so this has to always be negative. How about my determinant? So my determinant, so we can have minus A times by minus A. It's going to be A squared. Minus B times by B, it's B squared. So this is a little bit tricky this time because we're only told that A and B are positive. We're not told whether A is bigger than B or B is bigger than A. So what that means is the dynamics of the system are going to be dependent on the relative magnitudes of A and B. So we have that our determinant is going to be negative if A is less than B, and our determinant is positive if A is greater than B. So in this case here, if you were to refer back to the diagram that we had in the lecture, a negative determinant is going to give us a saddle. And if we've got a negative trace and a positive determinant, that means we either have a stable node or a stable spiral. How do I distinguish between these two? Yeah, so we look at our tau squared minus 4 delta, okay? We look at the sign of this. Remember, this is going to tell us whether we have real or complex eigenvalues. If we have any complex eigenvalues, that means we've got some sort of oscillation going on, okay? So what do we have here? So we're going to have tau squared, so it's going to be 4a squared minus 4 lots of a squared minus b squared. So if you expand this out, this 4a squared here is going to cancel with this 4a squared here. The minuses for the b's are going to cancel. So this just gives us 4b squared, which is positive. That means that we have two real distinct eigenvalues, which means that this can't be a stable spiral. Okay, so we have these two possible outcomes. Depending on the sign, but depending on the relationship between A and B, if A is less than B, we're going to have a saddle, and if A is greater than B, we're going to have a stable node. So let's again think about drawing what these look like, but we're going to have to split it into two different cases, okay? In case one, we have A is greater than B, and we're going to have a stable node at the origin. So once again, have a go at just finding your null lines. Find the direction field on your null lines, and then have a go at sketching this. Okay. So you should end up, when you do your null lines, you'll have two straight lines that go through the origin, but they'll be going through different gradients. Okay. Have a go at that. Okay. Let's start with the null clines, and then I'll give you guys a little bit of time to go over the direction fields, okay? So our first null cline, the RDT is equal to 0. That requires minus AR plus BJ to be equal to 0. I mean, all this is doing is it's coming from this equation up here. Setting this equation equal to 0 gives us the null cline for R. Okay, so if I set that equation to 0, I get minus AR plus BJ is equal to 0. Now I need to rearrange this. Now I'm going to have J on my vertical axis, so I usually find this is best if we rearrange in terms of J. So I can rearrange this, take the AR to the other side and divide by B. I'm going to get J is equal to AR over B. Okay, and then we have dJ dt is equal to 0. Looking at the second equation that we started with, here we had BR minus AJ is equal to 0. Again, if it's not clear, that's just setting this equation here, dJ dt is equal to 0. Yeah.
Would it make sense to also rearrange the null cline so that it's in terms of R?
You can totally do it that way. It's fine. It's just I find it easiest because this is kind of like doing y's in terms of x's when plotting things, and it helps me think about the gradients. But there's nothing wrong with doing it the other way around. Okay, so here we've got BR minus AJ is equal to 0. Again, I'm going to rearrange this in terms of j's. I'm going to have J is equal to BR over A. Okay, so these are just two straight lines. Okay, let's do this one in pink, and I'll do this one in green. Okay, these are just two straight lines. What are their gradients? Well, we know their intercepts are going to be the origin. There's no plus C term here. And we know also because it's a linear system, it's going to have to go through the origin. And we're told up here that B is less than A. So that means that A over B is going to be greater than 1, and B over A is going to be less than 1. So if you imagine if we have let's draw a dashed line. This is the line J is equal to R. A over B is greater than 1. So that means that my null cline, my pink null cline, let's go back to this, means my pink null cline is going to have gradient greater than 1. So it's going to be above this dashed line in the first quadrant. And then my green one, B over A is going to be less than 1. So the gradient here is going to be less than 1. Okay, so those are the two null clines that we have. What are my directions going to be on these null clines? Now the pink one, we have dr dt is equal to 0. So I know that we can only be moving up or down on the pink null cline. On the green null cline, the j dt is equal to 0, so there's no movement in the j direction, so we have to be moving left or right. Okay, have a go at finding the direction field, whether these arrows are going up or down. Remember, what we're doing is we're basically saying pick a point on either the pink curve or pink line or the green line. We know that in the case of the pink line, for example, dr dt is equal to 0. So we just have to look at the movement in dj dt. So we have an equation for dj dt from the original equations, and we have what our j value is on that line. So we need to substitute this j into my dj dt. And likewise for the other one. Doing that will give us something in terms of the signs of dr dt and dj dt in terms of r and j. Yes. The dotted black line is just the line j is equal to r. So this has a gradient 1. And the reason I put this on there is because we know that the pink null line here, because it has an a over b in it, and we know that a is greater than b, A over B has to be greater than 1, so the slope of that line has to be greater than 1. And in the second one here, B over A has to be less than 1, so the slope of that line is less than 1. So that black dotted line there is just to help me sketch this. Okay. Okay, there's just a few minutes left, so I'll run through this. So let's start with our pink knob line. So this is looking at on our line J is equal to AR over B. We know by definition that dr dt is equal to 0, which means we're not moving left or right, we're just moving up and down. What's our dj dt? Well, this just comes from this equation here. So our movement in the j direction is br minus aj. And we can eliminate the j here. You could eliminate the r if you wrote it around the other way. There's nothing wrong with doing that. We know that we're sat on that line, j is equal to ar over b, so we can substitute in this j here into our dj dt. So you have br minus a squared r over b. This is where it gets a little bit tricky. There's a little algebraic trick we can do here. If we take out a factor of, we have a common factor of r. If we could take out a factor of 1 over b as well, we can have a b squared minus a squared. So if you multiply this out again, you'll get the line above. Why have I done that? Well, I was told up here with considering the case a is greater than b. That tells me that this thing here is going to be negative, because a squared is going to be less than b squared. So what does that mean? That means that dj dt has the opposite sign to r. So dj dt is less than 0 if r is greater than 0. And it's going to be greater than 0 if r is less than 0. So if I go up to here, these arrows point down, these arrows point up. Okay, let's very quickly do the final one. So on j is equal to br over a, we have dr dt is equal to, in this case, we're going to have minus ar plus b times by j, if I remember rightly. Yeah. So again, we can substitute in j here. So we're going to have minus ar plus b squared r over a. Do the same trick that we did before, pull out a factor of r over a this time. We're going to have a minus a squared plus b squared. And this is going to be always negative as well. We've got a b squared minus a squared. So this tells me that r, dr dt, has the opposite sign to r. That means when r is positive, we move to the left. When r is negative, we move to the right. So if we sketch on an example of a solution trajectory, we'll go in like this, like this. Remember we had a stable node? Does that make sense? We knew it's a stable node from looking at our trace and determinant before. And our phase plane matches our analysis of looking at the trace and the determinant. Okay, so there's one more example of this, of the case where A is less than B. And we know that we have a saddle in that case. Have a go at doing that using exactly the same methods that we've just used now. See if you can use that, get to the right result. I'll post the solutions. Practice, practice, practice.